Hello everyone and welcome to This Explainer. I am incredibly excited to have you here today, mostly because we're looking at one of the absolute most fascinating challenges in modern technology. We're talking about bridging the gap between human intelligence and artificial intelligence systems. We talk a lot about the algorithms themselves, but today we're going completely under the hood. We're looking at the actual architectural blueprints, the support patterns for these learning paradigms that make seamless collaboration between humans and AI actually possible.
Okay, let's dive right into this because this is the core tension we have to resolve today. On one side of the equation, you have machine learning pipelines. They're rigid, they absolutely love structured batches of data, and they operate on strict mathematical schedules. But on the other side, you have human experts. And humans are brilliant, but let's face it, we are completely unpredictable. We go on coffee breaks, our opinions clash, and we definitely don't produce data on a neat automated schedule. So how on earth do you synchronize the two without breaking the whole system?
Well, to answer that, we're going to break this complex system down into a few manageable, logical pieces. We'll start with the innovation and market niche, then move into the two-layer orchestration framework, followed by human feedback processing patterns, and finally, wrap up with real-time and decentralized patterns.
All right, Chapter 1, Innovation and Market Niche. We really need to set the blueprint for why these specific systems matter so much for modern ML ops.
Now notice the core concept we're dealing with here, the boilerplate support pattern. When you're building these niche human-AI collaboration apps, you absolutely do not want to reinvent the wheel every single time. A boilerplate pattern is basically a parameterized code template. Think of it like a generic, highly adaptable architectural blueprint. By applying these proven templates across different systems, developers can massively reduce inter-system complexity. It takes away the headache of cross-system integration, acting as a huge accelerator for complex AI architectures.
So who actually benefits from these? Mostly, it's AI solution integrators, specifically teams building solutions around three advanced learning schemes. Active learning, where the model queries a human for labels, swarm learning, which involves decentralized network training, and neural symbolic AI. And the best part? These aren't just theoretical ideas drawn on a whiteboard somewhere. A major selling point is that these exact patterns have been practically applied and validated in the real-world scope of the HumAIne research pilots.
With that context in place, let's look at the foundation everything rests on. Section 2, the two-layer orchestration framework.
Think of this framework kind of like a highly efficient modern factory. The first layer handles the heavy machinery. It uses an Elira-based visual plugin sitting right on top of Kubeflow. That gives developers this great drag-and-drop interface to build sequential machine learning workflows, things like data fetching or model training, straight from their Jupyter notebooks. But a factory needs a nervous system to react to things happening in real time, right? That is the second layer, Node-RED. Node-RED is an asynchronous platform built specifically for event-driven integration. It coordinates real-time system interactions, processes user feedback, and talks to external messaging mechanisms. It's essentially the dynamic layer bridging those rigid ML sequences with the chaotic outside world.
Okay. Chapter 3, Human Feedback Processing Patterns. This is where we focus entirely on the human in the loop and how to manage that unpredictable asynchronous input.
Let me introduce you to the first real bottleneck, or kind of the villain of our story. Machine learning retraining pipelines are resource-heavy. They literally cannot efficiently execute every single time one human provides one piece of feedback. If feedback is just arriving asynchronously from all over the place, it's way too chaotic. The system absolutely must gather a critical mass of structured, batch data before it even makes sense to launch a new retraining session.
Enter the feedback aggregator pattern. Here's its mechanical superpower. First, it uses a publish and subscribe model over a topic-based messaging queue to collect distributed events right as they happen. Second, it uses key-based routing to group that incoming data together until a specific configured batch size threshold is hit. And once that critical mass is met, step 3 kicks in. It extracts custom metadata, appends key-value pairs, and uploads that entire data batch to an object storage bucket. The beautiful part is that that storage activity automatically publishes a notification, triggering the model retraining pipeline. No human intervention needed.
But look, to truly understand these systems, we have to be honest about the trade-offs. The aggregator pattern definitely has limitations. Because you're literally waiting for a batch size to fill up, this process naturally introduces system delays. If you're the first expert to submit feedback on a Monday and that batch doesn't fill up until Thursday, your early input is just stuck waiting in line. Which brings us to our next major challenge, and this one is absolutely critical. The feedback consolidation pattern deals with the simple fact that human expert opinions frequently diverge. Just imagine you have two highly trained doctors looking at the exact same complex medical image, and they disagree on the diagnosis. For an AI model, that is a disaster. It creates severe ground truth uncertainty and total ambiguity about how the model is supposed to behave.
So how does the consolidation pattern handle that divergence? Well, the system routes incoming expert views and groups them using a composite key, like matching a specific image ID with a patient ID. Then it runs a similarity check. Let's walk through the outcomes. If the opinions match, fantastic. The data progresses right to normal storage. But if a conflict or contradiction is detected between those experts, the message is instantly routed to an alert output channel so a human authority can step in and resolve the whole thing.
However, this pattern has its own kryptonite. It requires a static configuration defining exactly how many expert opinions the system is waiting for. If the system expects 3 doctors to weigh in, and one doctor goes to lunch, gets distracted, and completely forgets to click approve, the entire transaction is indefinitely blocked right at that validation point. It literally just waits forever.
All right, Chapter 4, Real-Time and Decentralized Patterns. What happens when we simply cannot afford to wait? We are moving to the edge here, dealing with real-world emergencies and distributed networks. We just talked about batch delays. Well, in real-time industries like manufacturing or health monitoring, delays caused by static batches can lead to genuinely dangerous operational mistakes. If a machine on an assembly line is about to break or a patient's vitals are dropping, you can't wait for a batch to process. Highly uncertain model predictions need to alert a human authority immediately. So here is the automated flow to solve that. The low-confidence expert notification pattern. As the model makes an inference, an API evaluates the prediction and injects its mathematical confidence rating right into the file's custom metadata. That file is pushed to storage, which automatically fires an event to an active webhook inside a Node-RED workflow. Instantly, Node-RED extracts that score to review it.
So the crucial point is this specific threshold number. If we configure our predefined threshold to be, say, 0.85, and Node-RED sees that the model's confidence has dropped to 0.70, it doesn't wait around. The pattern immediately publishes a warning message to an exchange topic. The designated human expert gets real-time alert, allowing them to step in and make a crucial judgment call right on the spot.
Now for our final architectural problem, swarm learning. In collaborative, decentralized systems, you simply cannot assume that network nodes or human experts will remain online 100% of the time. There's going to be technical dropouts, spotty internet, or opportunistic participation constraints. You need a rock-solid way to know exactly who is actively in the swarm before you start training. Mechanically, the swarm learning discovery pattern maps this out perfectly. First, any participating node declares its arrival or withdrawal by publishing a message to a dedicated fan-out exchange. Next, a specialized listener component captures those notifications, filters out any duplicates, and updates a central memory structure of active nodes. Finally, right before a swarm training session begins, a coordinating orchestrator executes a synchronous REST GET request. That fetches a perfectly up-to-date, verified list of active collaborators. Nobody gets left behind, and the system never stalls waiting for a node that went offline.
Which leaves us with this final, kind of profound thought. We often obsess over making AI algorithms smarter. But as we've seen today, seamless integration relies just as much on smart MLOps plumbing as it does on advanced algorithms. If this architectural infrastructure can flawlessly orchestrate human unpredictability, managing our delays, our disagreements, and our dropouts, what new paradigms of human-AI symbiosis are we ready to build next? Thank you so much for joining me for this explainer. Keep learning, keep questioning, and I will see you next time.